Okay, so next we'll talk about matching in general graphs. So let's look at some example. If we have such a graph that V is a cut vertex, and say if I remove V from the graph, then I get some components. Okay, and say these components are even. So a component is even or odd if the number of vertices in the components is even or odd. Okay, so I'm saying that I have something like this. So my graph is something like this, and so if I have such a vertex V that if I remove, then I'll get some components, and say I have this situation. So can we see something about matching, that can this graph has a perfect matching? Can this graph has a perfect matching? Why? Yes. So why it is not there cannot be any perfect matching, because this is even, so maybe everybody is matched inside the component, but here at least one vertex is we will not be able to match from the component, right? So for any odd component, one vertex will be remaining which I cannot match inside the component. So I have, because two odd components, that means I cannot match these vertices inside the component. So with whom I can match? With this center vertex V, that is the only choice, right? But I have two such components. That means there is no perfect matching, right? What if I replace this V with some set S? So I am saying I have some vertex subset such that I have some odd components. So for a perfect matching, what should I have?
The cardinality of odd components should be lesser than cardinality of S.
Anyone else? So think in the same way. So I had one vertex V and I had more than one number of odd components. That's why I am not able to match those odd components remaining vertices from V, because V is only one vertex, right? So what should be here?
Cardinality of S should be equal to the number of odd components.
Yes. So here number of odd components should be at most cardinality of S, because in every odd component there is something, there is at least one vertex which is left which cannot be matched inside the component, and so that can be matched in S only, right? Because in G minus S, after removing this, I am getting these components. So this cannot be matched with any other component, right? So the only choice to match these remaining vertex is S. I can match it in S only, and such a vertex exists for every odd component. So number of odd components should be at most cardinality of S, then only I will be able to match, right? So that means this is a necessary condition, okay? This is necessary to have a perfect matching. And now we will show that this condition is also sufficient to say that in a general graph there exists a perfect matching. Okay. So that is our next theorem, which says that, okay, so for number of odd components we will denote it as Q of G, and number of odd components in which graph I am talking about? In G minus S. So, after removing S, I have some components, so number of odd components there. So, Q of G minus S. So, I am denoting it as this. So, what is the theorem? That in a general graph, so given G has one factor or perfect matching if and only if Q G minus S is at most cardinality of S for every S subset of vertex. And this theorem is given by Tutte in 1947. Okay. Right. Let me check. Yes. Okay. So, forward direction, is it okay? So, forward is that it is necessary. Why it is necessary? So, suppose for some set, so for forward direction, let us prove forward direction. So, suppose for some set this condition does not hold, and we are saying that we have a perfect matching, and we want to show that for every vertex set this property holds. So, okay, it does not hold for some set. So, there exists some set S such that this one factor is perfect matching. So, there is some S which fails Tutte's condition. Okay. So, that means number of odd components in G minus S is strictly greater than S. What does it mean? That we have some S and here are some components, and say these are odd components. So, let us forget about even. For even we may be able to match everything inside, okay. But look at the odd components. So, for every odd component we have some vertex which at least one vertex cannot be matched inside, okay. At least one of them will be unmatched, we cannot match it inside the component. So, where this will match? Because we are saying that graph has perfect matching. So, everybody should be matched with something. So, they will match with S. What does it mean? That number of odd component, cardinality of S should be at least equal to the number of odd components, right. But we started with something else. We started with a set with this condition. That means there will be some vertex which we not be able to match. So, that means there is no perfect matching, because this vertex cannot be matched with anyone, because cardinality of S, many odd components I can match, but some odd component will be left with some unmatched vertex. Okay. So, forward direction is easy. So, let us think of reverse direction. Okay. So, let us we try to prove contrapositive statement, that suppose G has no one factor. That means there exists some set which fails this condition, right. That we want to prove. We want to prove that if G has no one factor, then there exists some set which fails this condition. Okay. Okay. So, let us assume, okay, not this. So let's assume that G has no one factor, and our goal is to find a bad set S. What is bad set? Bad set S such that Q G minus S is strictly greater than cardinality of S. So that is my goal, to find such a set. Okay. Okay. So we'll prove this for a graph. So among all those graphs G which fails this condition, Tutte's condition for some set S, I will take the graph which has maximum number of edges. Okay. So I am taking maximal edge graph such that this condition fails for some set. Okay. And we can do that, right? So given any G, I can just add edges till the point, like at every point I will maintain that there is some set which is still bad. So there will be some point when I will add one edge and the bad set will become good set. Okay. So I will stop there. So I am saying that given any G, by adding edges I can come up with a set which has maximal number of edges which fails this condition for some set. Okay. By adding edges. And this new graph, for this new graph, if you have some bad set, then the same set will be bad for the original one as well, right? So we can do, right? So let H be an edge maximal graph such that Tutte's condition fails for some subset of V. Okay. Okay. So suppose you have some set S. Okay, let's not write it here. Okay, now you have this some set S, and these are some components. So now how this graph will look like? What can you say about these components? This is edge maximal graph. Every component should be a clique, okay? Because I can add edges. Because it does not depend on the inside, what you are saying, that Tutte's condition. For this, we talk about the cardinality. We are not looking at the graph. So every component can be a complete graph. So for edge maximal graph, so we are saying that in H, okay, no, I am talking about this set S. So let S be a subset of Vg, then not G, this is H. So S has the following properties, that every component in G minus S is complete. Okay, these I can make complete. What else I can say? What about S? Also complete. And what about the edges going from S? We can assume that every vertex in S going everywhere is adjacent to everybody, because actually for Tutte's condition, what matters is the cardinality. Issue is with the cardinality, right? So that's why the second property in edge maximal graph would be that for every vertex in S, S is adjacent with every vertex. So S is adjacent with everyone. So this is how how this set and our graph looks like. So for every set, everything is adjacent. Okay. And these are complete. This is also complete. Okay. So if we have a bad set, then this condition holds. Even if it is not bad, then also it holds. Okay. So bad thing. Okay. Now I want to see. Okay. For any bad set, it holds. Okay. I said for any set it holds in edge maximal graph, right? So bad set it holds. Now I want to say that if this properties holds for some set, then I can find a bad set. So basically I want to characterize my bad set which I want to find by a set with this property. Okay. So I want to claim that if I am able to find such a set with these property holds, then I am done. I can give you a bad set. Either S will be that bad set which has this property, or I will give you something else. But I want to characterize my this finding of bad set with this property, with a set with this property.
When you say you give something else, is it because S is not a bad set? If G is not ordered.
Yeah, if it is not bad set, then I will give you some other set. If S is not bad, then I will give you something else from this. Okay. Yes, because that is our goal, right? So our goal is to find a bad set, and I am saying because edge maximal, H is edge maximal, then if S is a subset of Vs, then it holds this property. Okay. And now I am saying I want to claim that it is enough for me to find such a set which has this property, and I will give you a bad set. That was my goal, right? So for that I just need to show. Okay. So let S. So let's say these two properties, denote them as star. So I am saying that let S is a subset of H such that S satisfies star property. Okay. Then we are done. Okay. Or then we have a bad set. So suppose we have S such set exists. So either S is bad or not bad. So if S is bad, then that is my bad set which I wanted to find, and I found it. So I am done. So either S is bad or not. So, if S is bad, then we are done. So, let S is not bad. So, if S is not bad, what does it mean? So, I have this S, I have these components. So, for every even component, okay, these are even. So, for every even component, because each component is complete, so you can have a matching inside the component itself, perfect matching. So, for this you have a perfect matching. What about odd sets? Here as well, like you can have a perfect matching, not almost perfect matching. There will be some vertex here which is remained, and I will try to match it with S. Now, S is not bad, right? So, if S is not bad, that means the number of odd components is at most the cardinality of S, right. So, that means for every odd component I have some vertex in S with whom I can match with, because S has bigger cardinality than the number of odd components. So, I can match everybody, every unmatched vertex in the odd component from S. Now, what the remaining thing is? The other vertices, because cardinality of S is maybe bigger, right. So, you still have some remaining vertices. You can match inside, this is also a clique, right. But I started with a graph which has no perfect matching, right. So, I should not be able to match everybody. So, then what it implies? If I am not able to match everybody, what does it mean? So, count the number of vertices. Yes. So, if you count the number of vertices, then in the graph you have odd number of vertices, right, because in every even component you have even number of vertices. For every odd component you are matching it with somebody. So, this is again become even, including this. Now, the remaining vertices, if I am not able to match inside S, that means the number of remaining unmatched vertices in S is odd. That means whole G is odd. Is it okay? So, we are saying that if S is not bad, then it implies this. So, therefore, we can match every odd and even components every vertex in or let us not talk about even components. Matched with some vertices in S and match the remaining vertices inside S. Okay. But because this graph H has no perfect matching, but H has no perfect matching, right? No one factor. This implies, what does this implies? That the cardinality of whole vertex set is odd. Okay. And in that case, what is my bad set? Empty set. So, empty set and in this case this empty set is bad set, because you have not removed anything, but your remaining component, you have only one component which is G and which is odd component, and your set is empty. So, that means this empty set fails Tutt's condition. So, we found phi. Okay. So, by proving this claim, what we came up with, that now in this H our goal is to find such a set, because if I find any set which satisfies this condition, then I can find a bad set, either S is bad or empty set is bad. Okay. So, now the goal is to find such a set. Okay. So, our goal is now to find a set S such that S satisfies star property. Okay. So, here we know that S is a clique, right. So, we can start with, so let us start with some set, some vertex set S such that we start with the set which in which every vertex is adjacent with everyone else. Okay. So, I am starting with the set which is adjacent with everybody. Okay. So, such that for every S in S, S is adjacent with every other vertex. Okay. So, that means one of I am starting with a set with this condition, I can start with, right. Now, I want to show that every component in G minus S is complete. If I able to show this for this set, then this is the required set, right. Now, I want to show that every component in G minus S is complete. Okay. Okay.
So when you put this set to be a bad set, now that's your claim is, I think I missed something. Once you put this is a bad
So we started with that, suppose your graph has no one factor, that means there exists some set which fails Tutt condition. Okay. I am saying that set as a bad set, a set which fails Tutt's condition, that is a bad set. So, now my goal is to find a bad set. Now, I am finding a bad set, but first here I just characterize the, like, I have changed my goal. So, I am saying that now here I am saying that I want to find a set which satisfies certain property, and if I able to find such a set, then I can give you a bad set.
This is the characterization of bad set itself.
No, it is not a characterization. This is for any set. For edge maximal graph, that is what I was saying, that we start with edge maximal graph. That means all possible edges you can add until you have some set which is bad. You are not violating like this failure of the Tutt's condition.
Says that if you have a set from these star properties,
Then we have a bad set. Yes, then we have a bad set. We are not saying that the S set S itself is a bad set. It may be, but it may not be. So, this is not a characterization for a bad set, but for any set. I am saying for any set, if I can find such a set, then I can find a bad set. So, either S will be bad or S may not be bad, but in that case I can make sure that I have some other bad set which is empty set. That's what we talked about here.
Okay, now you are claiming that the set, how to find such a set,
Yes.
given it exists.
Yes. So if claim, after proving this claim, now I can make sure that I just want a set which satisfies these property. That's why I have proved this claim, because I know that if I have a set, then I have a bad set.
No, so in this claim, it is in H or in G? A bad set where? That is also.
In H, because in H, if I can find a bad set, then the same set is also bad in your original graph, right? It will be more bad maybe. Okay. Anyone else has any doubt in the current like goal? So we want to find a set which satisfies star properties, because according to this claim, if we have some set which satisfies star property, then we have a bad set. Either S is bad or empty set is bad. Okay. So I started with some set such that in S every vertex is adjacent with everybody else. Okay. So out of these two property, I have started with one property. Okay. I am starting with one, and I want to prove that for this S, every component is G minus S is complete. Okay. So suppose S does not satisfy this star property. That means suppose S in G minus S, there is some component which is not complete. Okay. So because I started with some set S, so either S satisfies this second property or it fails. If it satisfies, then we are done. So assume that it fails. Okay. So sorry, not second, first. We started with second property, and now for this set, I am saying that either this condition first property holds or fails. So if it holds, then we are done, right? We already have that set, and so we have a bad set. So now suppose that it fails. That means, so suppose there exists some component in G minus S which is not complete. Okay. So I have some component, let's say call it as say R. So I have some component which is not complete. That means, what does it mean? That there exists some pair A prime in this component R such that A prime is not an H. Okay. So look at some shortest path. If it is not adjacent, so let's look at some shortest path between A and A prime in the component. So let P be a shortest path, A to A prime path in R, and say P is some A, B, C, and it ends with A prime. So say this is the path, this is shortest path. I am writing very big, I guess. So I have this shortest path. So what does it mean? So this AC edge is not there in the component, right? Because this is the shortest path, A to A prime. So this implies that we have some edge AC, non-edge. So I have some non-edge in this component. Okay. So I have some missing edge here, which is not present. Now let's sum where this vertex B is. I took this path inside the component. So B is in not in S, right? So B is not in S. Okay. B is not in S, and in this path, because this is the shortest path, so there exists some vertex such that B and that vertex V is not adjacent. Okay, so I can find some non-adjacent vertex in this path. So there exists some D in R such that BD is not an edge. Okay, so I found one BD is also non-edge. Now recall that we started with a edge maximal graph which fails Tutte's condition. That means if I add one more edge to the graph H, then Tutte's condition hold for every subset, right. So that means in this graph H, if I add this edge AC, then it has a one factor. It holds Tutte's condition and it has a one factor. So that means H plus AC has one factor by edge maximality of H. Similarly, H plus BD, for this also we have a one factor. Okay, this also has one factor. One factor means perfect matching. So let's call we have a perfect matching in H plus AC, call M1, and in H plus BD we have perfect matching M2. Okay. Now look at actually in both the set only one extra edge is there. Okay, so in this graph, because after adding AC edge we are able to match everybody. That means here only like one edge is missing, right, in this M1. Same for M2 as well. So for same for M2 as well. So here what I want to find a path, some augmenting path. So I want to say that even if I don't have these additional edges, then also I will be able to have some path, some perfect matching. Okay, so what my claim is that I will try to find a cycle, because I know that this has one factor, this has a perfect matching, this in this graph also we have a perfect matching. I will try to find a cycle with alternating edges. That means it will have, it is even cycle, and it includes this new edge BD, okay, which is from M2. So I want to find some this kind of alternating matching. Okay. Yes, here.
But
if the path length is 2? No, but A and A prime is not adjacent, right?
Yeah, but AC A prime.
Oh, D is not necessarily in this path. D is not necessarily in this path. It is any graph, any vertex in G, right?
But then how can you claim this that is not an edge?
रुको. What?
Then how can you claim that BD is not an edge?
Because there exists some such vertex, B, some such vertex which is not adjacent to B. Because for example, A prime here, BA prime is not an edge, otherwise you have a shorter path.
Yeah, but B is not in the path.
B is in path. I started A, B, C. B is in the
I'm
path.
saying that the path is A, B, A prime.
A, B,
A prime.
A, B, A prime.
This is the path.
Okay.
Then how can we say there is a D such that BD is not an edge?
Hmm?
D may not be up from R, D from the B.
Hmm?
This D belongs to R,
Huh.
that is from B.
Yeah. Because B is not in S, B is not inside S. That means there exists some vertex outside. If not in this component, outside you can find some vertex which is not adjacent to it. Okay. So maybe inside S everything is adjacent to B as well, but in some other component you can find some vertex which is not adjacent with B. So it is not in the same component. It may not be in the same component, but in the whole set. But because B is not in S, that means there exists some vertex such that BD is not an edge, and this is not an edge is H. Okay. But B is in this path, okay, at least. So I want to find such alternating cycle, and what I want to claim is that in original graph G, I did not have this BD edge. So even if I remove this edge, then also I have such a path, right, which is alternating, which is augmenting path for M2, right. With respect to M2 matching, this is augmenting, and so I can augment it and have a matching M2 without BD edge. Okay. So the idea is clear. So what I want, I am saying that H plus BD has one factor, and so H plus BD has this perfect matching M2. Now I want to find such a cycle which has alternating edges from M1 and M2, and BD is present in that cycle. And if I find such a cycle, then I am saying that even if I remove this edge, which is because it is not there in my original graph H, in my starting graph H, then also I have some augmenting path with respect to M2, and so I can augment my matching and still can get a perfect matching, and which is a contradiction, right. So that is our goal, to find such path. Okay. So let's start with to find a cycle. Let's look at a
This D can be from this S also.
D can be from S also. No, S in S everything is adjacent with everyone.
Okay. So if there is no only one component after removing S.
Only one component after removing S. Okay.
Then how can we ensure this D
There
exists?
should be at least two components, otherwise.
No, not there.
Such D doesn't exist and D will belong to S.
You are saying that A B S prime, then B is adjacent with S.
Yes.
We are not choosing. S is defined as a set of all vertices where every vertex is adjacent to every other vertex in the graph.
We started with this set, no? Yeah. So we started with this second property, and now we want to show that first property also holds for this set. So what if it first property does not hold? Then we
Inclusion wise maximal.
hmm?
This should be inclusion wise maximal. Only then we can say if B does not belong to S, then definitely there will exist D. Otherwise, you can simply add B to S and we get a bigger set.
Yeah, so B is not in S because B is in the path and I took this path in the component. So B is definitely not in S. Okay. Okay. So now let's start with some maximal path and start with D. So we are starting with some maximal path starting from D and which has alternate edges from M1 and M2. Okay. Let P be a maximal path in H starting at D and having alternate edges from M1 and M2. Yes, because in S we started with that every vertex is adjacent with every one. So this will be adjacent, right? Or maybe you can find in the same component as well, we don't know. Okay, so from now I got these M1 and M2 perfect matchings in these graphs, but I will look at the graph H and find a maximal path which starts at D and have alternate edges from M1 and M2. Okay. So my path is starting with D and so these are my, and say it ends at V. So you are not able to further extend it, this is a maximal path, and this edge is, we are saying alternate edge. So where this edge will belong? First one, we
Is the same path B?
no, say P prime. Okay. So we are looking at a maximal path which is starting at D and has alternate edges from M1 and M2, okay, and it is in H. So what can you say about this first edge? Where it will belong? Because this has alternate edges, like one edge is from M1, then M2, then M1, then M2. So like this. So first edge, where it will belong? Either in M1 or M2. Where? M1, right? Because in M2 BD was there, but I am talking about H. So BD edge was there, which is not present here in this P. So that means this belongs to M1. Then this is in M2. This is in M1, like this, and this path ends at V. This is maximal path, you are not able to extend this path further. Okay. So now we have two cases. Look at the last edge of this path. Either it belongs to M1 or M2, right? Okay, so case 1 is that last edge of path P prime belongs to M1. Okay, so if it belongs to M1, what can we say?
Swap the edges of M1 and
Hmm?
swap the matching.
It is M2 augmenting.
Yes. But still, what you can say about this vertex B?
So it increases the matching M2 by 1. And M2 is 1 less than the perfect match. We got
It is B.
Hmm?
To be B. B should be
Yes. So look at this way, that every vertex is here. Every internal vertex is M2 saturated, right? This end point V is not M2 saturated, right? But M2 was a perfect matching in H plus BD. So what is the possible choice for this vertex V?
B.
B only, right? Because if BD is not there, then still M2 should be saturate every vertex in the graph except B and D. We started with D, so V must be B, right? So in this case, V is B, and that's what happened. Like B, this was B in this case, and this was the edge we were adding, and we able to find a matching which was perfect, right? So this is that BD. Okay, so in this case, V is equal to B, and so here we find this BDH. So what is perfect matching in this case? We want one factor, right? So what is one factor in this case? This is okay. Can I remove this part or that part? I'll remove this one, or I'll remove this. Okay, let's see. Okay, so what earlier I said that I want to find a cycle, even cycle with alternating edges. So here my cycle is this, which has alternate edges. So this is from M2. This edge BD is from M2. So in this first case, V is B, and so we found a cycle. We found a cycle C, which is what? The path B, P prime, path P prime, and it ends at B, and we add this edge. So this is, we found a cycle, okay, and this is, note that this is even cycle with alternating edges, because it has alternating edges, right? Every edge is either in M1 or M2. So okay, just keep the cycle for the time being and go to the second case. What if the last edge of P prime belongs to M2? What if it is in M2? What can we say about V? It is in M2.
Yeah, so for M2 we only have B and D as option.
Yes, but in this path, everybody is like saturated with M2. So we should look at M1, not M2. Yes, so V is either A or C, because in M1 we have a perfect matching, right? M1 is a perfect matching in the graph H plus AC. Now on this path, V is not M1 saturated. So what we can be? Either A or C, because if other than A or C, every vertex is saturated by M1, right? Because we have a perfect matching in this graph. So that means V belongs to, V is either A or C. Okay. Okay. So it is either A or C. So in this case, what would be the cycle? So you have this A or C. So less for the timing, I am assuming that it is A. It is A. Now look at here. A has a path. A is adjacent to B. Okay. One second. And see, BD edge BD is not present here, right? BD edge is not present in this path. So what I'll say that, okay, for this A I have some vertex B, and then for this B I have some path. BD is in edge, right? BD is edge in M2 in H plus BD graph. Okay. One second, I have some doubt. Should not be here, right? Okay. So from this path we know that AB is an edge, right? So now this A to B is, there is an edge, right? So this B, where it can be, this vertex B?
Because it's maximal Z.
It should be here because this is maximal, right? And B should be saturated by M1, okay? At least by M1 it should be saturated, if not by M2. Okay, so there should be some edge, B should be somewhere here, and BD, if I add this edge BD, so I have this cycle. So I have the cycle, what the hell, man, this P, A, B, T. Some problem is there. What is the problem? I wanted something. The issue with me is that the issue is like I want a cycle which is even cycle. Oh, can you all wait for 5 minutes? So let's complete the proof. This argument is left. Okay, so I'll take 5 minutes. So if it is A or C, so I'm saying if it V is A or C, I have some edge from this to B and take, so I'm saying that I want a cycle P prime, and P prime ends at V, which is either A or C, then A and C both are adjacent with B, so V, B and D. So I'm saying this is a cycle. This is an even cycle, okay, and this is alternating cycle. And I have not used the edge AC in this cycle as well. So basically what I got, that in both the cases I got an even cycle C in H plus BD. In both the cases I found an even cycle in this graph, not in AC graph. H plus AC.
So, if D is in the path,
Here?
yeah,
Yes.
then D is saturated by M2. Because one edge.
Oh yeah, so that is the point. Exactly. That's what I was thinking, like it should not be in the path. Okay, so but AB is an edge, right? So it
That is not possible, right? It's a maximal.
yeah, this is also not possible because it is a maximal path.
No, maximal alternating path. AB is not at all a matching edge.
But there is a perfect matching, right? So only thing is that AC is not present and BD is not present in this original graph.
But it's a maximal path and edge starting at.
They should be in M1. It should be in M1, right?
If it is in M1, then we can have bigger path. If it is not in M1, then we are fine.
It cannot be in M2. So either it is in M1 or it is not matching. But it should be matched, right? Because H plus BD has one factor. So if and H plus AC has one factor. So if H plus AC has one factor, that means in M1 saturates everyone in H except A and C. So B should be saturated by M1.
AB cannot be in M1 because AC must be in M1. Yes. AC must be in M1, so AB cannot be in M1. So you can add AB.
Yes.
So now we have BD. See,
What
repeat?
repeats?
Do the way
Hmm.
we can. AC must be in M1 and BD must be in M2.
Yes.
If AC not belongs to M1, then you have in H you may get M1. AC does not belongs to M1. That means H must have M1. Then that is not have a perfect matching. So AC belongs to M1 and BD belongs to M2. Now in this P dash, starting from D and last is D and A. Now AB does not belongs to M1 because already AC belongs to M1. So you have that H.
So you are saying, Satya, that AB is not in any matching.
No, AB cannot be in M1. AB cannot be any matching because BD belongs to M2 and AC belongs to M1.
But A will be matched by. Oh yeah, you're right. So in this graph H plus AC, we are saying that A and C are the only one who are unmatched in H, right? That's why H plus AC gives me a matching. But M1 should saturate everyone else other than A and C. So this A is not matched by M1 and nor M2 because M2 is there.
That's why this H.
Yes. So we get an even cycle. So because AB is an edge, but this does not belong to M1 or M2. But B and BD is also one edge. Okay. So but the point is that we found an even cycle in H plus BD. AC edge I am not taking. So even in H and H plus BD, in both the cases, I found one even cycle. Okay.
How come this even now? Like because you have a path. You
Because
have edge.
AB edge is also there and BD edge is also there. So up to this point you have even, right?
Yes.
Because you started with M1 edge and you are ending with M2 edge. So you have covered even number of edges and now you are adding two edges. So you are getting even cycle. So this is even cycle in H plus BD. Okay. So in both the cases you find we found an even cycle in H plus BD. So now look at M1. So can I have a matching in H? So in this cycle C, we have alternating edges, right? One from M1, one from M2. So if I remove this edge BD, then also I should be able to match everyone. So I am seeing that this I can match with M1. So in H plus BD we got this even cycle. Now if from this cycle I remove BD, then can I saturate every vertex with M1? That is what I am asking. So, in this case, if I include this, edge in M1, then I will be able to saturate everything in this path, and outside this path M1 already like saturating everyone, right?
Yeah, but it should not be part of M1.
It should not be.
Part of M1.
Here when we were taking this path, then we were saying that okay, it is not in M1, but now I want a perfect matching. I want a matching which saturates everyone even after removing BD. So, I am saying that in this C, huh?
It is an even cycle. Now the question is, without using BD, can you saturate all the vertex in the cycle?
Yes, and
Yes.
that you want AB to be a part of M1.
No, nothing. You have that even cycle. Only the extra edge is BD. So the question is, without using BD edge, can we match every vertex in the cycle? We
Yeah.
can, because it is an even cycle. Yes,
Because
yes,
how
yes,
would
yes,
you
yes,
how
yes,
would you
yes.
do the
Yes, yes,
vertex? So you have to include AB in M1.
AB in N1.
Yes.
Now we have to include AB in M1. So, we get this even cycle. Now, I am saying that I have a matching. What I am doing from this cycle, I am removing BD and all the edges from M2, and all those edges I am making matching edges for this new matching. Okay, and outside this cycle, whatever vertices I had, whatever M1 I had, I am taking all those edges in my new matching. Now, claim is that this matching is perfect matching. Okay. So, if this is perfect matching, then that is a contradiction, right, because after removing BD, without BD also, I gave you a matching which is perfect. So, that is a contradiction, right, because we started with the graph which has no perfect matching. We started with the edge maximal graph H which has no perfect matching, and then we were looking for this set S. So, we started with this set S satisfying second property. We said okay, first property, let us check whether first property holds or not. If it holds, then we are done. If it does not hold, then there exists some A and A prime in that component which is not complete. Then find a path between A and A prime. So, we found this path A B C A prime. Now, we are saying that okay, because this is shortest path, so AC is not an edge, and because B is not in S, so then there exists some vertex in the whole vertex set such that BD is not an edge. Now, we say that because we started with edge maximal graph which fails Stutz condition, that means if I add one more edge, then it should satisfy all the sets should satisfy Stutz condition, and so H plus AC has perfect matching. Same for H plus BD, we have some perfect matching. We say okay, M1 and M2 are the perfect matchings in these graphs, and we start now looked at some maximal path which is alternating in M1 and M2. Now, we had two cases that where the last edge of this path belongs to. So, either in M1 or M2, in both the cases we gave we found some even cycle which includes the edge BD, okay, which includes the edge BD. Now, in both the cases I am just removing BD and giving a new matching which does not include BD and which also saturates every vertex. And so, we are done with because we found a perfect matching in H, which is a contradiction. So, that means that S was the required set. Okay. So, this is okay. This you can see from here, even if AB is not in M1 in the second case, but we can include this in our new matching. All the edges which were in M1 on this path and this edge AB as well, I am including in my new matching, and outside this cycle everyone whichever was saturated by M1, I am taking the same matching. So, now this new matching is perfect matching. So, you can just see this claim for yourself. This is simple, I guess, but still, because we don't have time. So M has a M prime is a perfect matching in H, which is a contradiction. Okay, that's it. And if you have any doubts, then you can ask in the group. Okay, so you can just go and read it through, and if you have any doubts, then ask.